We'll finish our notes from yesterday, and then we can start 5.5. We'll start and finish 5.5 today. Maybe start a little bit of review, and then Monday review, Tuesday quiz. I think we finished, we stopped yesterday at example 4. So we'll move on to example 5. All right, first things first. Can we move things around and just clean up some of these terms by moving things around? Yeah, denominator. We're stuck too many terms in the denominator. Now, if it's e to the 2x, we can move that up, change the exponent, and try to merge with the numerator. But yeah, we're kind of stuck here. So second option is use substitution. So here are some of the new rules that we've been learning here. All right, so we want to find a suitable u value that will lead us towards one of the existing rules. And maybe it's the 2x. Maybe it's the e to the 2x from the numerator or denominator or both. Or maybe it's the denominator in full. What do you think will be the best fit that will lead us towards our rule here?
The entire denominator.
Okay, entire denominator. Okay. So if I let the entire denominator be the u value, we should be able to make our way to this 1 over u. Let's talk about why these other two options are not going to be quite enough. If we let our u value be 2x, then we're left with e to the u over e to the u, and that's not going to make it look similar to this, but still too much hanging out. So we're not going to be able to make much progress. This is not enough. The e to the 2x, I think if you pick the e to the 2x in the denominator, that's a better progress, because you're thinking that the e to the 2x will cancel out when we get to the derivative. But then you're left with 1 over u plus 1. And even 1 over u plus 1 looks like this. It's not a perfect match. So the e to the 2x is not going to be enough. Okay, so we target the entire denominator. Okay. Okay, we find our derivative. Okay, what's e to the 2x's derivative?
E to the 2x times 2.
Good. Keep track of that exponent's derivative. There's a little bit of a chain rule there with that u prime. The 1 goes away. That's just a constant. Cross multiply and see where we end up. Oh, let me underline the parts that we're targeting here. Divide the 2e to the 2x over. Make our substitutions. All right. What do you see here? Except for the 2, which we can push out as 1/2. Okay. Now, once you get past that 1/2, we should get a perfect match with a rule that we can use. And we do. All right. Cover up that 1/2. There should not be any changes with our rule that we want to use. Okay. All right. That's just going to be natural log. Bring back our variable x. All right, any questions with 5? All right, number 6. We have integral of 2e to the x minus 2e to the negative x all over e to the x plus e to the negative x. If we try to move things around, denominator is not easily movable because we have multiple terms added together. So we're kind of stuck in this form. We're now maybe look at our second option, which is use substitution. Let me list out some possibilities here. Maybe the u is the x or the negative x. Maybe it's e to the x or e to the negative x. Maybe it's the numerator. Maybe it's the denominator. All right, what's going to fit and move us towards one of our rules here? Okay, probably the denominator. Okay, I think we usually want to think of the u value as something that's a little bit larger, but that 2 maybe is kind of throwing us off because we're like, well, is that denominator going to be enough to handle this? Looks like a larger expression here. But we do know that derivative of e is just going to be itself, so at least we have that going for us. And we're looking in the right spot. So yes, that's going to be our target here. And I know there's a 2 here that makes it look like a larger value, but maybe down the line we can factor that 2 out and we can get the rest to match up. So as long as we have a portion of it matching up, if we factor it out through multiplication, we can still look to cancel out. Okay, these other options are just not enough. Okay, we're almost never going to be just involving u with just x. Sometimes with negative x, but that's usually for kind of smaller problems. There's too much going on here where that's not going to fit. E to the x is also not enough. Imagine replacing all these with u's. You're still not going to be able to make it match one of our restrictive rules, and there's only a few, right? So we got to make it match one of our existing rules, and it's got to match to the t. Numerator is not a good spot to look, so okay, we look at the denominator there. All right, derivative. E to the x is just e to the x times 1. How about e to the negative x?
Negative e to the negative x.
Yeah, so e to the negative x, we always are going to have the exact same problem as part of our derivative, and then the exponent's derivative. So negative x becomes negative 1. So now if you look, this negative 1, we can push this out in front, make it a minus, and that's also a good sign because if you look at the portion that we have left alone, we eventually want this to kind of transform into some version. So having that sign change is going to be helpful, right? We're going to be able to get a better chance of it matching up here. We solve for dx, move the we look to make our substitutions here. All right, we're getting closer to our goal. What can we do to handle those remaining x's? Yeah, so maybe that will be enough for us to get a match here. So let's take a 2 out, factor a 2 out of this numerator expression. Yeah, that change in sign is helpful, right? Now we're able to get that sign to match. Everything matches inside the parentheses. We factored a 2 out. Take these 2 terms, matching pairs out. All right, there's still a 2. We can push that 2 out in front, but once that 2 comes out in front, we should be able to get our target there. All right, once we're here, we can apply our natural log rule. And then let's bring our x back. All right, questions? All right, next section, 5.5. We're looking at exponential functions, base A. All right, just want to recall some of these derivative and integral rules and just seeing some connections here. We just got done talking about exponential function e to the u, base e. And we know that the derivative for e to the u is just e to the u times u prime. And we knew that if the derivative process left our function unchanged for the most part, then the integral process will bring us back without much change either. So that's why our integral of e to the u is also e to the u. Okay. The reason I'm having this to start with is because I want to show you that exponential functions a to the u is going to have very similar properties. We can kind of think of e to the u as kind of like a parent function, and a to the u is slightly different. It's a different base, but it's going to follow very similar patterns here. So a to the u is an exponential function. Exponential functions are where your base is a constant, and then or a numeric value, and then your exponent is a variable. So the reason why we say a to the u is because all bases other than e kind of follow the same pattern. So base a, depending on the problem, it could be 2 to the x. That could be base 2. It could be 3 to the x. It could be 12 to the x. It could be 9 to the x. All right, as long as we have a positive value, we're able to. So all these different bases all fall under this category of what we call a to the u. So if I want to find a derivative of something that is in the form of a to the u, there's a conversion that has to happen, and that conversion into base e is going to be a natural log of a. But then after we get past that conversion, our pattern will look very much the same. We're going to be involving the original function, just like with e to the u, with its original function, times the exponent's derivative, times u prime. So that's the derivative rule for a to the u. And the reason why I want to show this to you is because our integral is basically starting here and working our way backwards towards our original starting point. So notice how there's not much change here, right? A to the u's derivative is a to the u. So if I take the antiderivative of a to the u, it should bring me back to the a to the u. But then the question is, what happens to this natural log of a? So if I'm starting with a to the u, and if I end up at a to the u, this natural log of a has to go somewhere. So it's going to end up being divided over and it's going to end up being divided where it's going to end up in the denominator. So that's why integral of a to the u is going to leave us with 1 over natural log of a times a to the u plus c. We're just basically starting here, moving backwards, and then dividing that natural log of a over, landing in the denominator space. So here's example 1. As a reminder, natural log of a is just a constant. So we're going to treat this like a coefficient. It's just going to be a number that's going to hang out in front of our variable expression. Okay, 2 to the x dx. We see that this is a nice match with our a to the u. This is base 2. This is an exponential function. I'm not going to have to go through u substitution because it's just a simple u equals x. So I'm just going to follow this rule, replace every u with x here. So my rule just says 1 over natural log of 2, that's my a value, times the original function, a to the u, which is 2 to the x, plus c. Okay, starting with a simple, just matching the parts for from our rule. Okay, number 2, we have 3 to the 4x. Let me write that a little bit larger here. 3 to the 4x also falls under the category of an exponential function, but now it's base 3 raised to an exponential variable. But now we should go through u substitution because we have something a little bit larger than just an x. So we'll target the 4x being our u value. Let's make our substitutions here. 4x becomes u, dx becomes du over 4. Okay, it's getting closer towards our rule. Let's just push that 4 out in front as 1/4. Now we got basically a perfect match. I mean, once we get past that 1/4, we have a specific base. My a value is 3, and now we can jump into our rule. Okay, questions so far? Now, something to keep track of is that sometimes with these problems, you may have to deal with some multiple coefficients. So just want to make sure we understand that there's a 1/4 that's going to be in front, and it's also going to be this 1 over natural log of a that's going to be in front. So you're going to have some multiple coefficients that we got to make sure we include. So I'm going to start off with a 1/4. That's the first thing I see here. And now I'm going to get into the rule. So the rule first starts off as 1 over natural log of a. My a value is 3. So 1 over natural log of 3. And then the rest of it, the original problem, 3. My a is 3, so 3 to the u plus c. Okay, we basically have our answer. Just replace the u back in terms of x. And this is just my preference. I see some multiple fractions here. I'm going to just push it to be one fraction, but you don't have to. Yeah, I just like to leave any coefficient, especially fractional coefficients, out in front. For me, it just looks cleaner. But you're welcome to put this below the 3 to the 4x, and that's perfectly fine as well. All right, any questions? 1 or 2? All right, a little bit more involved here with number 3, but I think it still matches nicely with our rule here. I have 5 to the tangent of x times secant squared x dx. I think it still matches up pretty nicely, right? What's our u value?
10x.
10x, right? And we leave that secant squared x alone, hoping that the tangent derivative will take care of that secant squared down the road. Okay. So our derivative for tangent is secant squared. I have a formula sheet that's available under today's link, so feel free to print that out. I'll also include this on your quiz and test. I'll attach it to the back of your test and quiz. So derivative of secant of tangent, is secant squared. Okay, cross multiply here. Okay. Replace the tangent, replace the dx. I'm left with secant squared above in the numerator, the secant squared x below in the denominator, so pairs up nicely. No coefficients to keep track of. Okay, we're left with integral of 5 to the u du. And we just follow our rule from here. And then let's bring back our variable x. Okay, questions with 3? All right, let's go to 4. I'll put this on a separate sheet, just may require a bit more room here. All right, looks messy, but is it still going to match up nicely with our new rule here?
Should.
Okay, it should. Okay, what do you think as a u value that we could use?
3 minus x squared whole exponent.
The entire exponent. Yeah, let me point that out here. Some of you may be thinking that maybe the 3 minus x is enough, but here's the thing is that if we want to use a to the u or e to the u rule, we have to let the entire exponent be the u value. If we let the u value be anything less than the entire exponent, let's say it was just 3 minus x, then you're left with 7 to the u squared. And in the end, you're not going to get that match that we want, right? U squared is not, right? You're adding something, you're changing something from the rule that's available. And we can't just adapt it and say, well, that's u squared here, so I'll put a u squared there, right? So this is very restricted, right? It's got to be a perfect match. We can't add and, change things here and there to adapt. We're very restrictive with how these rules work. So we're going to have to look at the entire exponent. And the hope is that once we find this derivative, it will handle this 3 minus x nicely. Okay, we'll see what happens. Now, let's find the derivative. Going back to first semester here, what do you think is involved when we want to find the derivative of something in this form?
Chain rule?
Yeah, this is chain rule here. So it's a reminder. Chain rule has an outside and inside portion, and we take turns with each of those portions. So my outside is the parentheses squared, and the inside is the 3 minus x. All right, so let's take care of these one piece at a time. Yeah.
Could you just expand it because it's a difference of 2 squares? Or
Yeah, that's right. Yeah, yeah. You could fold this out and avoid chain rule. That's perfectly fine. I'm just having us practice with that chain rule because if it's any other higher power, right, you just prefer to use the chain rule. But yeah, but you're perfectly fine in expanding this, doing power rule, and then bringing it back. Perfect. All right, so just practice though with the chain rule. What's the outsize derivative?
2.
So we're done with the outside. What's the inside derivative?
Just 1.
-1, right? Okay. 3 goes to 0. Negative x becomes -1. Where does the -1 go? Outside. Good. We don't want to fill this in, right? This is something else. So times -1. All right. What goes in here? Yeah, the original, right? The original inside is going to. Okay. Cross multiply. I'm going to pull the negative in front of the 2 here. And I'm going to solve for dx. But let me ask you this. This is kind of like a minor point here. Should I distribute the -2 through?
No.
Okay, what's useful about this form? Yeah. Whenever I'm doing a derivative, I'm always looking back at my problem and seeing, okay, am I making my way towards what I have a goal in mind, right? I'm always looking to see, is this going to work out? So leaving that -2 there and the 3 minus x in its own parentheses is kind of a good place to be because we see a 3 minus x, so we're hoping that this will just match up nicely. If you distribute the -2 through, you're going to have to factor that -2 out again. So yeah, looking ahead into the problem can kind of help save a little bit, a few steps. All right, dx, let's see, solving for dx. All right, make my substitutions here. Just going to replace what I highlighted. All right, so having the 3 minus x visible is helpful. We see numerator, denominator is going to have that match that we want. Coefficient, -2, let's not lose track of that. Push that value out in front. And we should have a nice clean match here, right? So the -1/2 starts off our answer with -1/2. Then we move to our coefficient within the rule. And then the a to the u. I'm going to merge these fractions together. You don't have to. And then finally replace the u back in terms of x. All right, questions before? Okay, let's skip number 5 and we'll go to number 6. All right, what's different about this is we have bounds, right? But we talked about from the last unit that even if we see bounds, we're going to pretend like the bounds are not there because that's not there's something that we need to do before we do the bounds. So I like to rewrite the problem. Just allow me to focus on the task at hand, trying to get that antiderivative. And then once we find the antiderivative, then we can worry about the bounds, right? This is where if we go through use substitution, we're going to have to match, find compatible variables, either u's with u's or x's with x's. So we'll practice with that. So first things first, though, looks like we have a match. We can go through use substitution. Okay, what's our u value? Yeah, entire exponent here. So we'll start the problem like we've done in the past with the other problems here, and pay no attention to the bounds. Not yet. Now x over 3, I'm going to rewrite that as 1/3 x, just easier for my power rule. So derivative is just going to be 1/3. dx equals 3 du. Make my initial substitution, 4 to the u times 3 du. Can I put this together and make it 12 to the u? Yeah, operations, right? This 4 is kind of stuck within this form here. That 3, best we can do is push it out in front, but we can't make that 3 multiply with the 4. Okay, I think we're ready to apply our integral rule. Keep the 3, 1 over natural log of 4, 4 to the u. All right, we have our antiderivative. I have it in terms of u, and I'm going to explore the possibility of working in the bounds, but there's some adjustments that we need to make. So this is the first method. You can choose between these two methods. Method 1 is getting everything in terms of u. So right now, we have to understand there's a mismatch. This is our antiderivatives in terms of u, but our bounds is in terms of x. So I'm going to look at my lower bound first and move on to my upper bound. So if x is equal to 6, the way that we convert is we look at that assignment that we created between u and x. And that's how we move between the two variables. So if x equals 6, then u is equal to 1/3 x, which is going to be 1/3 times 6, which is 2. So our updated lower bound is 2. We're going to push the -12 through that conversion process as well. My upper bound is -12. Which is -4, so my updated bound is -4. Okay, questions so far? Now that we have a match with our variables, bounds are in terms of u, my antiderivative is in terms of u, I can go through the process. Upper bound first, followed by minus sign, then lower bound. Is this going to be an issue where my upper bound is a smaller value than lower bound?
No.
Okay, it's okay. It's okay that everything will work itself out. We're not restricted that, because these are out of order, that we're going to get the wrong answer or we need to adjust it. You can adjust it, but typically I don't worry about adjusting it because the process is going to be, it's just an additional step. If you want to flip the bounds, you can, but you got to change the sign and it's just an additional thing to do. But there are times when I do change the bounds, and that is when I'm trying to read the graph. If I'm trying to look at a graph and try to add up things from left to right, I like to have my bounds in order, so I don't have to change the sign of what I see in the graph in front of me. But typically, if I'm just working it from a calculus perspective and no graph in front of me, I'm just going to just going to whatever is upper bound, I'm just going to blindly plug that in, followed by lower bound. Question?
Oh, yeah, why do we not include the plus c?
Okay, so with definite integrals, what's going to happen is there are plus c's that will show up, but the plus c from this is going to disappear once we subtract the plus c from the lower bound. So there's a plus c from the result from the upper bound, there's a plus c from the lower bound, but it's all just going to wash out, so we just always just ignore it. But we do have plus c's for indefinite integrals because we're creating a general equation, so we need that plus c there. All right, so here's the result that we have here. Upper bound gets evaluated. I'm going to push this to be one fraction here. Upper bound gets evaluated, followed by lower bound. Leaving your answer unsimplified is fine by me. So this, as messy as it looks, that combined is just a number. So I'm good with you leaving your answer like this. Okay, that's one method. The second method is we bring everything in terms of x and evaluate it from the x's perspective. So if I want to do that, I'm just going to take my antiderivative and take it one step further, bring in the x into my antiderivative. And if I do that, then I can use my original bounds because my original bounds is already in terms of x. So here's method 2. Okay, so I took that additional step, replaced the u with 1/3 x, and then I can rely on the original values in my bound. Put -12 in for x, I get -12/3, which is -4. Lower bound in for x. Six in for x, 6/3 is 2. Okay, if you look, same results. Okay, questions? Now, many of you guys may prefer method 2, which is fine. The reason why I keep showing method 1 is because I just want you to be comfortable with this method. On the AP exam, a lot of times they like to work on multiple choice. There could be a problem where they want to see if students are able to work through that progress and make the appropriate selection in their answer. And you have to have knowledge of converting the bounds in order to reach that point. So. All right, let's look at some mixed reviews on the back of the notes page of 5.5. Okay, so let's start off with number 1 here. This is off the mixed review. All right, back to square one here. Can I rely on moving things around and combining terms?
No.
All right, denominator, we're stuck, right? Too many terms. All right, second option, use substitution. What could be a u value that will help us move towards one of our integral rules?
The whole denominator?
Yeah, entire denominator. We see the denominator, well, first off, is a good place to look. Second, we see the degrees are compatible. X squared, we know we'll take care of that x. The x will go away to a constant. The constant will go to 0. Now, I know we're seeing a lot of problems where we're always replacing the denominator. It's not always the case, but I think it's a good place to start. We have some instances where we may only pick a portion of the denominator, but usually if you're just dealing with a rational function, I would say for the most part, it's going to be the denominator. But if you're dealing with natural log, with e to the x, maybe could be just a portion of the denominator and not the entire denominator. Ultimately, there's variety in what can happen, but the ultimate goal remains the same. You're trying to pick a u value, and in a way that will lead you towards one of the existing rules, right? So that ultimately is our big picture, and however way we get there can follow along different paths. But at least I can provide some general guidelines, so you can kind of follow those guidelines, but then just understand that we may have to veer from those guidelines, and we may have some exceptions to some of those rules. All right, so we let our u value be the entire denominator. Okay, du dx. Cross multiply. All right, that's a good sign, right? That 6x plus 5 showing up is helpful, right? We know that. All right, we should be able to get a clean match here. Do that one additional step here. Okay, so I got dx by itself. Replace dx with du over 6x plus 5. Perfect match, no coefficients. So I'm just left with 1 over u du. And I can apply my rule here. And then bring our x back. All right, I have one more for us. Okay, let's do number 2, and then we'll end there. Number 2. First things first, can I rearrange any of the terms? Too many terms in the denominator separated by plus, so we're kind of stuck. Second option, use substitution. Is it maybe 3x? Is it cosine of 3x? Is it sine of 3x? Is it the entire denominator? Yeah, that denominator I think is going to be a good fit here again. That 5, we can imagine it just going away. We can imagine that sine will turn itself into some version of the cosine, and having that denominator get completely replaced is just going to be a natural fit for this 1 over u that we may target. So, yeah. All right, derivative of 5 plus 2 sine 3x. 5 goes to 0. Okay, all right, what about 2 sine 3x? What does that become? Times times 3. Okay, careful, right? There's that u prime. There's that little chain rule there. We don't want to forget about that 3x has an impact on the derivative. Okay, can I merge anything here? Yeah, 2 and 3, right? Careful, when this 3x is inside the cosine. We can't touch that 3x, but we can move that 3 in front and put it with the 2. All right, that's a good sign. Cosine 3x. We're looking ahead. We should be able to get things to cancel out. Okay. Cosine 3x, numerator, denominator. Keep careful though. There's that 6 that we need to keep track of. Okay, I got a match. And then don't forget, bring your x back into your answer. Okay, any questions? Okay, good. Monday, we'll do our quiz review. Help session Monday morning, 7:30, afternoon, 3:30, Tuesday morning, 7:15. Your quiz is going to be Tuesday, the 9th. If you can't attend help sessions, I'll record those, so hopefully that could be beneficial to you. All right, thanks everyone. Hope you guys have a great weekend. See you Monday.
Mr. Yang, I have a question.
Yeah.